All right, so how's everyone doing today? Good. How's the pace of the course? So after 2 weeks, if you're still enrolled, that's good. There's a few dropouts, but hopefully you're having some fun with the assignments and the Kaggle and everything. So let's look at, so lecture 6, some logistics. We have assignment 2 due this Friday. And just want to check, how's the Kaggle? Has everyone made a submission? Yeah. I saw that there are some submissions, but I don't know if everyone's made a submission. But do make a submission, and it's a fun way to know where you stand, and also if you can make improvements in your approach to the Kaggle contest. Yeah. Mini project 1 will be assigned this Friday. So assignment 2 finishes, the mini project 1 is assigned, and then we do 2 weeks later. So after assignment 2, you're going to have mini projects. There are going to be 3 of them, and each of them will be 2 weeks duration. So you get a good amount of time, but a lot of there's going to be a lot of stuff as well to do. So you're going to have 2 weeks worth of stuff. So we'll probably break it up into 2 milestones, like a intermediate milestone 1 week after the project is assigned, and then you have the final milestones that are due 2 weeks after the project is assigned. So we'll break it up so it's easy for you to do a whole bunch of things, and also not postpone it to the last minute. If you were to postpone it to the last minute like a regular assignment, you'll see that there's too much stuff to do and you'll not be able to catch up. So that's why we've kind of broken it down. So mini project 1 is going to focus on embeddings, sentence BERT, probably talk about it next lecture. Semantic search, we've already spoken about this, and yeah, it's designed to be more in depth than a regular assignment. So, but yeah, it's fun. You have different components to the mini projects, and as you do it, you'll have fun as you uncover the learnings and insights. So paper presentations are begin today. So the last 15 minutes of class. Can I see some show of hands, those who are presenting today? Okay, that's one team. Second team. Third team. So Arnav, we have 3 teams today? 4?
We should have 3 teams, yeah.
Okay, so third team is not here yet. You're the third team? Yeah. You have a team member? Okay, the 2 of you. Okay. So as you all know, the paper presentations are pre-recorded and uploaded to a Google Drive, and you'll be evaluated on the clarity of presentation. Like, is what you're presenting something that all of us understand here? Is it easily accessible? Do you have enough examples? Well, not enough, but at least a couple of examples to illustrate what the concept is about. I guess there's a template that was provided by Arnav. So even if you follow that template, you should be able to have a good structure and flow to your presentation. And also you'll be evaluated on your responses to Q&A. So we'll have 2 questions for every team based on the topic, and so you'll also be evaluated on it. So yeah, good luck to those who are going today. You're the brave ones, kicking it off today. But I think it's going to be a lot of learning. I mentioned it last lecture as well, but it's going to be tons of learning because we're going to cover so many papers across the whole quarter, and it's going to augment what we're covering in class. So it's going to be a fun ride. So that's on paper presentation. Anything else? Okay. Cool. So last lecture we looked at a recap of embeddings and cosine similarity. We didn't actually look at what glove embeddings are, but we used it in a search demo, and we also spoke about simple ways to compute sentence embeddings from word embeddings. So today's lecture, we'll go a little bit into the word to vec, but on the first word embeddings, and glove embeddings are coming in from here, kind of an extension of this. We'll look at an application of like embeddings in a business context with product to vec. Some embedding theory, and then we'll jump into transformers. So transformers will cover over 2 lectures, or maybe 2 or 3 lectures, the foundations. One is today's lecture, a little bit more high level and just kind of walk through. And then next lecture will be like going into multi-head attention and the components and the math behind it. So we'll look into all of that in the next lecture. And we may or may not have time for sentence transformers. If not, we'll cover in the next lecture as well. So that's the plan for today. Obviously, we also have the presentations at the end. So a couple of references for deep learning and sentence BERT are listed here. You can take a look when you have the time. Let's go to word2vec. So word2vec was one of the first, you can say, embedding models that came out in the literature, and it kind of created it ruffled some feathers, or it created some excitement, because you could answer things like, what is king minus man plus woman? Like you could do what they called word arithmetic using word2vec, right? And so we looked at this example earlier, but so let's look at a little bit on how the training itself is done. Word2vec is based on a skip-gram model. So gram refers to like words or combinations of words, like n-gram. N is equal to n equals 1 is like just a single word, and n equals 2 is 2 words, and so on. So skip-gram is you skip a word and you look at relationships. So let's say the source text is the quick brown fox jumps over the lazy dog. So training samples would, like with skip-gram, would be obviously you look at something that's next to it, the and quick. But you also look at, you skip and then you look at the and brown. So you look at how frequently do words co-occur within a sentence or nearby. Or you can even say, let's look at 3 words away, because that kind of gives you the context. If you talk about quick and fox, they show up together, and somewhere fox should have an embedding component that's connected to quick, because it shows up a lot in the documents, right? So that's the idea of not just looking at the next word, but also looking at the words nearby within a sentence or across sentences, and saying that these two, they should kind of co-occur, or we see them a lot. And so you can just take a sentence and create training samples and say, okay, the and quick should come together, the and brown comes together. And you can also have negative training examples and say these two don't come together. They don't, like you can have random negative examples as well. So you have positive and negative training examples, and you learn embeddings to predict for the positives accurately, and so have a high cosine similarity or high prediction for similar or co-occurring words. And if it's not so co-occurring, then you don't have a high score. So that's how the training is done. But the beautiful thing about this is you don't need a human to label these examples as positive or negative. It's learned implicitly through the sentences and the documents that you go through. So it's kind of like self-supervised learning, where there is supervision, but it's you're extracting examples from the text itself, right? Whereas in explicit supervision, you'd have to say, well, this is positive, this is negative. You'd have to give that explicit label. But here it's implicit, it's derived from the sentence itself, right? Because of co-occurrence. So co-occurrence is a implicit training signal or positive signal. We also saw implicit signal with Netflix recommendations. When you spend enough time watching a movie or a series, it must be that you like it. Otherwise, why would you spend so much time? So that's an implicit signal where you're not explicitly supervising or saying this is a positive, but you're implicitly deriving that information. Okay, so this is just one sentence. You can have multiple sentences, and that could come from a document, and you could have multiple documents, and so you can, the corpus of training samples that can come in, people typically start looking at Wikipedia, say, okay, let's look at Wikipedia documents, and then start generating extracting these sentences, and then extracting these training samples, put them together into positive and negative classes, and then train the embeddings to predict for this. So that's how you get informed embeddings. The embeddings are not random, they're informed based on the training data that it sees. Okay, so Wikipedia corpus. Okay, so yeah, I think when you look at the architecture, so let's say the input vector is across words. So in word2vec, we didn't have the idea of like tokenization necessarily like we see with LLMs. So let's say we just encode words, and then this is like a bag of words model. So where, yeah, this is called a bag of words. So you have a bag of words, and you say which words are present in the sentence that you're looking at. So here, if I'm just looking at ants, the index corresponding to ants would be 1, everything else would be 0. So that's bag of words. So it's very highly sparse representation. And if I've already learned these, I go through hidden layers here, and then if I look at the last but one layer, this kind of gives me the embedding for let's say here ants, right? So I might have layers in between, and then I go through, and then this is the output layer where you actually say that this is close to something else. So this is where your training data comes in, and you want to associate quick and the quick and brown and so on. So you given a word, you try to predict the other, and so that's coming in the output layer. But the layer before that, so this is the last but one layer. So that's what gives you the embedding for a particular word. So you just pass that, you have a bag of words, and then you pass it through this neural network, and then the last but one layer, you extract the activations, and that's the embedding. And whatever the dimension is, that's the embedding dimension. So in this case, if it's 300 neurons, your embedding dimension is 300. So that's kind of the architecture here. But this idea extends, the idea of like extracting embeddings from a neural network through the last but one layer extends to anything else, like extends to transformers, extends to OpenAI embeddings. So how do you extract embedding? It's just the same. You go to the last but one layer and extract the embedding from there. Yeah. Okay. So people would show that the word-to-vector representation actually works by mapping it. So here the latent dimension is 2. Obviously your latent dimension would be much higher. But let's say you had to map it in 2 dimensions. This is word-to-vec done on documents that are connected to programming. So you can see a lot of programming tokens are clustered based on semantic similarity. Like you can see there are so exceptions are coming in here, and then you see truth, and then you see the types are coming in here. Numbers are clustered together here. So a lot of it makes sense. So you can apply to different concepts. Like this is for programming, you can apply to other concepts, and then you can see visually that it actually makes sense. So that's where embeddings are powerful, that they can semantically cluster the words based on their embeddings, and similar words would have locations on the map that are close to each other, right? Okay. So let's do Hofei's here. Okay. Hofei, have we set up the in-class exercise? Yeah, people have tried 1, 3, 5, and then, so there are different versions, and then people have experimented with it. But the idea is don't just look at the next word, but also skip and look at something, because sometimes words are followed by prepositions and stuff, and they may not actually be connected. Like the quick brown fox. So the and quick, they actually don't have a relationship. So I want to skip, and maybe same thing with the quick brown fox was. Fox and was don't have a relationship, so I might have to skip and see what else. So, but it's not that I'm only skipping, but I'm also considering words next to it. But it's important to also skip and look at words that are nearby, not just right next to where you are.
So in general, one word skip between words.
People have used 3 and 5, so up to 5 words around both ways, and then you create training samples out of it. So started with 1, but have gone to 5.
What do you mean by both ways? Wouldn't the negative direction just give you the same results as when you go a little bit forward?
Yes, you would. It just depends on if you're using the input to predict to the output. So if the directionality matters. So if I say quick brown fox, so brown and fox or fox and brown, right? So if the directionality matters, then you want to consider both ways. But if brown and fox is sufficient, and if you have fox, would you predict brown or quick? Or if you had quick, you would predict brown fox, right? If you want to have the directionality as well, or it doesn't matter, then you would want to consider it both ways. Okay. Wait, does that answer your question? So let's look at an example in a business context with products. So product awake is an idea where if you wanted to understand what products are similar to each other, regardless of their actual category labels or internal definitions or classification that a company might have, this can give you a window into going beyond just categories. Although categories are a good start to understanding how products cluster, but you wanted to understand product clustering based on maybe shopping behavior or some other kinds of signals, then these embeddings can help inform with that. So the idea is the same. You take every product and then have an embedding of that, and then you can see that they tend to cluster in a way that makes sense. Like all the soft drinks and water and everything come together, cleaning comes together, and then cereals come together. So this is in 2 dimensions, but obviously the same thing. You can have embeddings in hundreds of dimensions. So you can apply this to product awake. So here's another example that's a little bit more deeper than just representing the embedding is, and something that I worked on when I was with one of the companies is, let's say you want to build a shopping cart and you already purchased a product, or you've already added something to cart. The question is given, let's say I added the cereals. If I've already added cereals to a cart, and let's say I'm doing grocery shopping for a whole week or maybe a couple of weeks, I just want to stock a whole bunch of stuff. Given that I've already added cereals, should I add coffee next or cereals next? What do you guys think? Coffee, right? I've already decided to go, maybe you like multiple brands of cereals, maybe, but maybe you want to cover the base first. Okay, I've already added cereals, so let me go to something else. So the embeddings can also help you with what we call diversification. So you don't want to just, these two are similar to each other. So if I just use similarity, I will just keep adding similar things. But I actually want to flip it and say, let's look at not so similar things. Again, I can use embeddings, but instead of a high cosine similarity, I'm looking at a lower cosine similarity as a way to add things to my cart. Obviously, I don't want to add random things. It should be something I'm interested in or something I like to purchase, but I want to diversify within that scope. I have a scope of products which I think I would like to add to cart, but I just want to diversify in there. So it has to be relevant yet diverse, right? So idea is you want to have relevant products, but with diversity. So yeah, and one way to capture diversity is through the volume. This is when you're building a set. It kind of helps to see quantify what diversity means. You can have diversity between two products is easy because you just look at the cosine similarity or is lower, then it's kind of more diverse. Like for example, here the angle is higher. So the cosine similarity between these two products is lower. So that's a diverse product with respect to one. But what if you had a set of products? What if you had like 5 products? How do you measure diversity of a new product in relation to the 5 products you already added to cart? So that's where the idea of volume comes in. So you can look at the volume of adding a particular item to an existing set of items. And so the more the volume, the more diverse your set is. So let's say you have more volume from this product, then you add it, and then so on and so forth. You can keep building your cart. So we're not just talking about 2 products, but let's say you have to build 10 products or 20 products into your shopping cart and then purchase it. So that's how you can take the idea of cosine similarity, flip it, and use it for diversity instead of similarity in a business context. So that's one application of embeddings in a product context. Yeah.
So the embeddings themselves are created by looking at like the text description and those kind of things?
So yeah, I think in these kind of examples, fresh embeddings will be created based on product information and other signals that are available, like even behavioral signals, because you have a whole business around products. So it's not just the description of a product, but also how they relate to other products based on customer behavior. So use those signals and again train a neural net to say these products are similar based on these signals, these products are not so similar, and then the last but one layer of that will again give you the embedding based on the signals that you specialized for your products, right? So yeah, even now people do this even with, I mean, even if you have like a large language model based embeddings, you still tend to specialize it for your company's context or your business context to get more accurate similarity measures for business use cases. So even if you had to use your, let's say, a RAG model within your company, the embedding retrieval component, retrieval based on embeddings component, that would be built internally so you can have a more accurate representation of products. Yeah.
When you say volume, do you mean like you create a specific convex shape for volume, or how is volume calculated?
Yeah, so that's a good question. I'm not going to the details of it so much, but here it's based on the similarity matrix between the products. So let's say you had, so let's say we're looking at volume, right? So if we have X as the embeddings, so you have, let's say, product 1, product 2, product 3, let's say product K, and then this is the embedding dimension, let's say 128. So this is a number of rows by column, so 128 by K dimensional matrix, right? The similarity matrix is when you take the dot product of the matrix with itself, okay? So when you take the dot product matrix itself, then it is shown that if you take the determinant of this matrix, that gives you a sense of volume of the vectors. So if you had like 3 vectors that are very spread out, the volume is higher. You kind of make it closer, the volume is lower. So this is captured through, can be captured through the determinant of that matrix. So there's some mathematical details that are kind of left out, but so you're actually optimizing for the volume of the through the determinant of the similarity matrix, and you're saying when I add a new item, is it increasing the volume or not? So it's a greedy algorithm, and it's also submodular. So anyway, so this is a little bit of mathematical detail, but yeah, the core idea is use embeddings, but then also encapsulated within this measure of volume, and then you can expand your set. Okay. Okay. Any other questions on this? So like we said, this class is not just conceptual, not just coding. We also want you to connect it with problems that you see at work. So we'll have this periodically from time to time, every other class. So let's break out into groups of 3 or 4. And we looked at X, here X represents any object. So we looked at product to vec, we looked at word to vec. Can you think of other X's in your company or in your business context for which you may want to build an embedding, custom embedding? And how would you do it, and why would you do it, and how would you apply, how will it help you gain insights for your business or for your product line? So just kind of see if you can brainstorm along these lines. Maybe pick an application area, and then what data sources do you have access to? And then how would having an embedding for that object of interest actually help you with your application, right? So maybe we'll spend, let's see how much time. Someone said bug to vec. Yeah, if you wanna identify bugs that are similar to the bug that you've noticing right now, maybe you can find solutions that are similar. That makes sense. I think people do that. I'm very sure companies do that. So maybe we can take 10 minutes, find 2 or 3 people you've not sat with before, groups of 3 or 4, and we'll come back in 10 minutes. Okay. Hopefully you had a chance to discuss. So maybe we can list out some X's that have come up in your teams.
I work in the blockchain space. We get a lot of telemetry. So the different elements coming down from the rocket can be different things that we want to cluster. Now, I was also talking about this idea of looking at user interaction with the system.
Okay.
Gain information about the interface.
Okay.
If you rely just on attributes or tags.
So can you kind of quantify what you said? What would be the object?
The object would be to given one problem that you're interested in, figuring out what's all the information, all the data points coming to solve that problem.
Yeah, but see, like we are looking at product to vec or word to vec. So the object is product or word. Telemetry to vec. Okay. Nice. What else? You guys, news to vec? And I think someone said bug to vec as well. What else came up? You guys?
Synopsis to vec.
Synopsis. In any specific context, or?
I think it's content or
Like I work for iVideo and health and safety, so we are doing auto rated sometimes, so PG-13 or R for different movies. So have synopsis to that can help rating a movie.
Oh, interesting. So how do you generate those synopsises?
Usually they come from the publisher.
Okay.
Yeah, but we also have other machine learning methods to just process the entire video and things like that. So I think this is a simple way to help.
Okay. Anything else?
So we have a bunch of one is customer behavior, like browsing behavior to vec.
Okay.
Another one I think it was image. Image to vec, image to vec.
Okay. Nice. Very cool. Yeah. So you can think of. So obviously, it's not that every time you have a new object you have to build an embedding. You try out existing embeddings. Like you can try out OpenAI embeddings and see if it's working for you. If not, you want to fine tune it. That's where you fine tune and build your own vectorizer, right? Or if you have very specialized use cases where you have a lot of requests coming in for specialized use cases and you want to be very accurate, so that's another reason to train your own vector model and get better embeddings. One thing I want to clarify here is, like, someone asked and brought up a good point, is like in the context of product to vec, while we fill up this cart, what if all in the goal of optimizing the volume or maximizing the volume, we fill up products that we're not really interested in because it's very diverse. So idea is that you always have to trade off diversity with relevance. Relevance is the most important component of recommendations and rankings and filling these cards. Is like, it has to be relevant to you, otherwise why would you recommend that? But it's like, if it's very relevant and I just keep recommending the same thing, like sometimes you go to a shopping site and then it says, okay, because you purchased iPhone or whatever, and it'll show you something very similar, but you want more diversity there so you can actually pick different things. So similarity is great, but then if you want to build a basket or you want to build a whole pantry of recommendations, then you want diversity. So we definitely want to keep the relevance in mind, but trade it off with diversity. So it's a trade-off between the two. Okay. And relevance would come from a different model. So you'd have a relevance ranking model or recommendations model. So you'd get a relevance score. And then from a diversity, you get a diversity score, and then you have a trade-off. You see which one maximizes the combination of relevance and diversity, and then you pick products based on it. Okay, here's another in-class exercise. So consider a company that sells products online. As we know, embedding representations for words or products are learned from data. So the question is, which data to use? So this is what we spoke about earlier on, using signals that you get at your specific company or in your business. Yeah. So question is, let's say we had two signals. One is view similarity. So view similarity is when two products are viewed in the same session, they are view similar, right? And then purchase similarity is if two products are purchased in the same session or close to each other by a user, that's purchase similarity. So the question is, for the purpose of representing products with embeddings, which provides a better signal, view similarity or purchase similarity? So here's an example, right? Let's say I have a product, biotin, and I want to get other products related to this item, or something like this. I want to build some carousel like this, and I'm using embeddings to retrieve these products. So the question is, should I use view signals or purchase signals to train my embeddings and generate those embeddings? Okay, let me take 30 seconds to think about it. Okay, so what's your answer? Yeah.
Purchase similarity.
Purchase similarity. Okay. Anyone else? Purchase similarity. View similarity. On this side, anyone? Yeah.
I think it kind of depends on the customer. Some people like to do more research. Some people just like to add everything to their list.
So you have to ask what the embeddings are meant to do. Like, if they're meant to cluster products that are similar to each other, if that's the goal, then view similarity makes more sense, because you view similar items in a same session, but you can purchase very different items in the same session. So from the context of getting embedding representations that are close to each other for similar products, view similarity makes more sense, right? Because I come into a shopping site with a particular intent. I'm like, I think I'm looking for something for my backyard. Let me look at backyard tools. And then I start viewing items, right? But then when I start purchasing, I might say, oh, I also want to get a paper towel in addition to this other thing. right? So when you time box a session, it might, you might be looking at products that are similar. When you go to the final purchase, you might start remembering things that you also want to purchase, but are not necessarily similar to the ones that you already added to cart. Does it make sense? Yeah.
Wouldn't it be easier to like poison the well of viewing similarity though? Because you could just randomly look at a bunch of different products, but purchasing different products requires intent to spend money to do it.
Yeah, I mean, they could be like, so this is about typical user behavior versus like some people might actually jump products when viewing, but you're looking at averaging behavior. So across a whole bunch of customers, is view similarity better or purchase similarity better? An individual customer might actually jump around a lot because that's their personality or they like to look at different things. But you're averaging over many, many such sessions, and then you can also time box a session. Like I'm looking at a 1 minute view similarity session or a 2 minute. So within that time box session, what is the averaging behavior? Is it for view similarity? So that's how you kind of pick the signals and then use it for embeddings. Okay. So again, it varies. This is not like this is like you have to again look at your context. So definitely depends on your specific application. Okay. Let's look at a few more things before we jump into transformers. So we spoke about this last time as a simple way to generate sentence embeddings from Glove, which is like a variant of word to vec, is to just average the embeddings. And we said this has a problem because it doesn't capture the sequence information. Yeah, so here's an example. Suppose you have two sentences, me loves my friend, and my friend loves me. They have the exact same words, right? And they have a similar meaning, which is it's connected to the sentiment of love. So should they have the exact same embeddings? No, right? Because there's a directionality. One says this person loves this person, other says no, that person loves this person. So, so the directionality is different. So you wouldn't expect that they have the exact same sentence embeddings. And we looked at this example before, which is more differentiated because, say, I like chocolate milk, I like milk chocolate. The first one's referring to milk, the second one's referring to chocolate. So they're different objects. But both of them have the exact same set of words. So in both example 1 and example 2, the set of words in the two sentences are exactly the same, but the implied meaning is different. And so we want embeddings to be able to differentiate nuances like this. So the embeddings have to capture sequence information. And so simple averaging of word embeddings wouldn't do the job to differentiate nuances like this. Okay. So that's where embeddings based on transformers come into play, because they can capture the sequence of information. If you go back to the history of deep learning, in one of the lectures we looked at, RNNs and LSTMs are deep learning architectures that were one of the first architectures that could capture sequence information in a sentence to some extent, to some limited context window. But they weren't very robust to large context or multiple sentences. So this is where transformers come into play. So let's look at transformers. This is from the famous paper, I think it's from 2017. It's called Attention is All You Need. It is a breakthrough paper, has tons of citations, very, very popular. And it came up with an architecture for encoding and also decoding or generating tokens. And it's surprising, it's already been like 9 years, but the fundamental transformer architecture hasn't changed much since this paper. Right? There have been a lot of variations, but the essence is still the same. So it was definitely a transformational paper, and it was on transformers. So in this graph, you see there's like two components. One is encoding, and the other is decoding. So the idea is that you have inputs and you want to encode it using some embedding and some token representation. You tokenize it, and then you have token embeddings, and then you represent the input in a certain format, and that's encoding. And then you pass the encoding to a decoder, and you also generate an output. So if your task requires that, you do that. Sometimes a task only requires encoding, and you can do classification on top of it. Like that's an example with your assignment 2, right? In assignment 2, you're looking at Yelp ratings. You don't need to do decoding or generation. You just need to do classification. So you can just use the encoder part, add a linear layer on top of it, do a softmax, and then predict the ratings 1 through 5 for your Yelp classification. That's part of your assignment 2. So depends on the task. Do you want to use encoding or decoding? So that used to be the case. Nowadays, decoders like transform, when we talk about LLMs, sorry. So nowadays, when you talk about LLMs and decoding transformers, they're very powerful that you can even do encoding tasks. But that's a separate topic. Anyway, going back, so we'll kind of break this. We'll look at both encoders and decoders in the next 2 or 3 lectures. We'll break it down into focusing on encoding and BERT, and also decoding and LLMs and llama models and GPTs and stuff. So we'll kind of go into the details and depth of each of these architectures and see how they differ and where they differ and what's the intuition behind different components of these transformers. Okay. So we'll begin with encoding transformer. And BERT is based on this architecture. And you can see here that there is this n times, which is like there's n such blocks of 2 components within each block, which is multi-head attention and feed-forward neural network. So this is kind of replicated across a number of blocks. If you look at Llama 3, it probably has 64 such blocks. So it used to be like people were looking at 4 or 8 blocks in the beginning, but nowadays the transformers are so deep, and then each of these blocks themselves have multiple heads and stuff. So we'll not go into the details of each of these, but we'll look at more high level today, and then we'll stop for presentations, and next lecture we'll kind of dive into the multi-head attention and look into the mechanics of it and understand it better. But going back to the input, so the typical way to encode an input from a sentence is to convert it into tokens and also generate token embeddings, and then also generate maybe position embeddings. Segment embeddings are optional. If you have multiple sentences, then you can segment it. But these two are definitely used with modern transformers, is token embeddings and position embeddings. Obviously, the part of tokenization is to convert words into subwords or word pieces, and then those become your building blocks. So your words are no longer your Legos or building blocks. Your tokens, that depends on your tokenizer for that particular transformer, becomes your building blocks to represent your input. And then the building blocks, each of the building blocks has an embedding, right? So whenever you train a transformer, instead of having word embeddings, you have these building block token embeddings that are learned as part of the transformer training. And so that kind of is already learned, and then you generate embeddings for each of these. And position embeddings are also present. We'll look at position embeddings. Position embeddings is the transformer's way of incorporating if it's milk chocolate or chocolate milk, because in milk chocolate you'd use position embedding 1. In chocolate milk you'd use position embedding 2 for milk, right? So that's how you can. This is the part where you're able to differentiate the sequence. The sequence information is incorporated using the position embedding. Yeah. Okay. So let's look at maybe an example. There's some terminology here. Okay, maybe we'll look at the terminology first. So let's look at some terms. Encoder is the architecture component of the transformer that transforms input through a series of neural network layers into an embedding, and this vector can then be used for downstream tasks, for emotion detection, classification, etc. So this is something we're doing in assignment 2. where you have a GPT-4 Nano and you also have BERT that's fine-tuned. But you take the last token, CLS token, and then you add a linear embedding on top of it, and then you add 5 classes and say predict between the 5 classes. So this is something we're also looking at assignment 2. That's an encoder. Decoder is the architecture component of the transformer that transforms input one at a time to generate words in a sequence. So when we ask a question of ChatGPT and it starts generating words, it almost looks like it has it all figured out, but it's generating it one token at a time. So everything is like next word, next token prediction, right? So that's decoder in action. Input embedding is what we say when we refer to the whole sentence and then the embedding that's coming out of that. That's the input embedding. So typically, you would say that's kind of the last layer, the CLS token, that can be an input embedding for an input. Token embedding is like the individual token embeddings, we already spoke about it, or subword embeddings. And then segment embedding, this is an optional thing which, if you want to compare pairs of sentences and say if this sentence is related to the other sentence, you want to segment it differently, you can add a segment embedding. So that was also part of the original transformer architecture. And it's an optional thing to include in modern day predictions. Okay. Yeah. And we also have sentence BERT and sentence BERT embedding. So these, we'll look at this in the next lecture. Yeah, so BERT embedding is when you've actually gone through the whole encoder architecture, and then you look at the CLS token, or you look at the mean pool or average of the last layer embeddings. That's kind of the BERT embedding. So when you look at OpenAI embeddings, you say, okay, this is the OpenAI embedding. It's 1500 dimensions. It's gone through all those layers, and then you take one of the tokens, and then you look at that 1500 dimensional vector and say this is the embedding for the sentence. So that's what OpenAI would do. So that's the idea here with BERT or sentence BERT embeddings. Okay. Any questions on the terms? Okay, let's look at an example. So let's say we had a raw input sentence. I love machine learning. It has 4 words. At this stage, it's just a string. There's no math. There's no tokenization yet. So typically with BERT, there is like text normalization. So if you have like uppercase, like I is uppercase here, you lowercase it. There's some other white space cleanup and stuff. So pre-processing. We're still in the text domain. We've not tokenized it yet. And then there's word piece tokenization is typically used for BERT. There are other kinds of tokenizations. Word piece tokenization is where you take a word and break it into subwords and prefix continuations. So for example, unhappiness is un and hash happy and hash ness. So hash is that it's like a subword, and there is something that's before that, because you have a lot of words that end in ness. So you might as well have a token for hash ness that kind of says there's a word for which ends in ness, right? So that's kind of how that's part of like creating tokens. That's a separate topic. So yeah, so we decompose words into subwords and word pieces, and these get mapped into tokens, and each token has an ID, token ID. So that's the next step. And there's also special tokens added. There's always for encoding specifically, we have a CLS token for BERT because it's bidirectional. For decoders, we don't have a CLS token typically, but so we add a CLS token that's like the start of a sentence, and then if you have 2 sentences and you want to separate it, you have a separator token. And these also have their indices assigned. And because you've now broken it down into word pieces, and then you added the start token and the separator token, and they all have their mappings to indices, you can now convert the sentence I love machine learning into a vector of indices that looks like this. So this is like the CLS, this is separator, and then these are the word piece token indices, right? And ahead of time after training, you already have mapped these indices to specific embeddings, right, that are fixed. So once you know the token ID, you also know the embedding. It's already in memory. So you kind of just load it in once you identify what the indices are. And you take each of these token embeddings, and then you also add in a position embedding. So CLS is position 0, and then you have I love machine learning, so this will be I would be position 1, love would be position 2, and so on. And like we said, segment is an optional thing. If you want to differentiate sentences, you can also add a segment embedding. So your final embedding is your token embedding plus your position embedding plus your segment embedding. And position embedding is fixed regardless of the sentence. Like if a token comes in position 2, it has this specific embedding and you add it on, right? So that's fixed based on the position. And then token embedding is fixed based on the token ID. So it's like a hash map. Given an ID, you have a token embedding. And same with segment. Okay. So each of these could be of a particular dimension. For example, with BERT, you could have 768, or mini BERT has lower dimensional embeddings, 300 something. So 768. So you just sum up these things, and then you get a 768 dimensional embedding. So at this point, you actually get a matrix of dimension 6 by 768, because there are 6 tokens, including the start token and the separator token. You have 6 tokens. And then each of them has a 768 dimensional embedding. So now we're just dealing with a matrix. Now we don't no longer have any words. We're just dealing with numbers, and they're all that's a matrix that you've obtained, right? Now, because you have a matrix, you can just transform it. You can do matrix multiplication and everything. So now we've gone from the word space to a matrix space where we can manipulate matrices and do a whole bunch of math and then get an output and then classify based on that. Okay. So then we pass it through transformer encoder layers. So BERT base, for example, has 12 identical transformer layers. So they're identical, but the input coming into each of those identical layers are different because they've already been transformed, right? So it's the same layer, it's the same kind of transformer, but then you kind of have different inputs for every layer. So every layer has multi-head attention, and it also has a feed-forward neural network, and then multi-head. So we look at attention a bit, but there is 2 concepts in attention. One is self-attention and cross-attention. Self-attention is when you look at how I correlate with other words in the same sentence. And then cross-attention is when how do I correlate with some other sentence and then the words present there, or some other sequence and the words present there, right? So self-attention is just looking at how these things correlate with each other. Yeah. So feed-forward neural network, it applies a nonlinear transformation independently to each token vector. Nonlinearity is key, with deep learning, even with early deep learning, if it was shown that you can almost learn any function if you have enough number of layers and enough number of neurons. If you remember, we looked at a TensorFlow demo where we saw really complicated data representations, and they could be learned with enough number of layers and enough number of neurons per layer. So nonlinearity and number of layers is kind of the game that's being played out here. So feed-forward neural network is kind of doing a nonlinear transformation there. And there's also this component of residual connections and layer norm. This is more for training to make sure gradients don't diminish, and the training is stable. So it was introduced more for training purposes, that there's stable training. But the key components are feed-forward neural network and multi-head attention. Multi-head attention is also something that you can say where I can understand myself in the context of all the other words in the sentence. So I'm able to capture sequence and relationships between different tokens much better because of attention, right? So let's look at, maybe we'll look at an example of the flow of attention in a bit. Yeah. So once you've gone through all the layers, let's say in BERT we have 12 identical layers. So we've had the tokens gone through all the layers. Because BERT is bidirectional attention, even the start token has information from all the other tokens. So if you want to understand what this sentence represents through an embedding, you can even just look at the start token, which is kind of counterintuitive. Like, let's say, okay, how would the start encapsulate information from the end? That's because the attention is always. So even the CLS token understands the whole sentence because it's getting attention from all the other tokens, right? So that's why people also just use CLS token as your embedding, and then you can build a new linear layer on top of it and make predictions like you're doing in assignment 2. You can also average embeddings between all the tokens, but you'd get similar performance. You don't see very different performance. Okay, so like we see here, this is kind of what we're doing in assignment 2, is we have a review, let's say a Yelp review, you pass it through a BERT model, and then you take the CLS token and add a linear layer, and then do a softmax, and then classify it into categories like 1 to 5 rating, for example, for Yelp. So that's kind of what we're doing here. Okay. Let's look at, it's reasonable. So I looked at a couple of sentences here. Let me see, did this change? Oh, it's changed, okay. Let me see if I can redo this. Okay, let's say this is, I just change the sentences here. Yeah, so we're looking at BERT base uncased, and there's a specific tokenizer for that, BERT tokenizer. Then we have 2 sentences, and we encode both the sentences, and then there's input IDs, and then there's token type ID. So we looked at this, and then we want to look at the attention between in a specific layer. So that's all of this stuff. Okay, so let's look at this. So this is layer 0. So as you can see, there's a CLS token, and then we have a separator because we have 2 sentences here. The rabbit went hopping quickly towards the finish line, and then there's a separator. The turtle crawled slowly but won the race, and then there's a separator. Okay, so attention says how are any of these words connected to the words here, right? So this is self-attention, and then this is cross-attention. So you can also look at, so let's say I look at sentence A, sentence B. This is cross-attention because I'm looking at how are words here connected to the words here, right? So let me see if there's some of them. So quickly here, I see some lines going to slowly, but rabbit is connected to turtle. Finish is connected to race. It's also connected to one. The lines are a little bit very blurred. I think they're not visible, right? You can't see. Okay, I can see it. It's a little bit unfortunate. Let's see if we can. Okay, can you spot? Okay, you can spot some lines here. So rabbit is connected to hopping, it's connected to quickly, it's connected to the finish line. So kind of makes sense, and it doesn't have too much cross attention to other words in here. Let's look at turtle. A turtle is connected to crawled, slowly. It's connected to one as well, one and race. So you can see when you look at a specific word, what else is it connected to, and how do I put it in context of everything else? That's kind of what self-attention is actually looking at. Because when I ask questions and say, who won the race, right? Then you look at turtle, it's connected to 1. There's a connection to 1 and say, okay, I think turtle won the race, right? And rabbit lost the race. It might not be obvious in a sentence on who won the race, but because of the attention and connections, the model is able to infer and make a good guess on what the answer should be, right?
Every word in that sentence is connected to every other word.
Yes.
Right?
Yeah, so it's an n square. If you have a sentence, that's why computing attention is a little bit expensive, because you want to connect everything to everything else. So that's with encoding attention. So with decoding attention is different, but with encoding attention, and BERT is bidirectional encoder, so there's always.
And so what it's learning is the thickness of that line, right? The square.
Yeah, there'll be different weights, and you can think of it as like how relevant is a particular word in the context of the whole sentence to this particular word. So obviously turtle would be relevant to turtle, but you want to see what else is it relevant to. So it's relevant to race, it's relevant to crawling, it's relevant to going slowly and all of that. So that's kind of the idea, is you want to understand a word in its context. So you look at self-attention there. And then this is in layer 1, and then you can go through different layers, and then the connections get more and more refined. So with BERT we have 12 layers, so that's why you have 0 through 11. So these connections keep changing as we go down the layers. And then you get and then your CLS token, like we said, as we see here, it's connected to almost everything here, right? So that's why at the very end, when we just take the embedding representation for CLS, it has relationships to all the other words, and it kind of encodes the semantics and the meaning and understanding of the important words in the sentence in the embedding that it captures. So that's why you can actually just use the CLS token, the start token, to make predictions. Yeah. So I think this is linked, so you can take a look yourself. You can play around with it. There's other visualizations in here that you can also play around with. I think it's a nice package that's here. Okay, so that's a little bit about attention. We'll go more into attention in the next lecture.